Welcome to Study Loop.
So here we are given an ideal gas that is inside the cylinder, and first it is at the state 1 that is sketched over here, and in this state the gas is under pressure P1 but on a different volume, V2. We'll call the volume V2. So the force is being exerted on the cylinder and the gas is being compressed. Under compression, the gas will increase its pressure, but the volume will be different. This is the second state 2. So on a pressure volume diagram, let's say that here is the point 1. The corresponding volume is V2 and corresponding pressure is P1. This is all being done on a constant temperature. So this temperature is going to be equal to T equals 65 degrees Celsius, or in kelvins this is going to be equal to 338 degrees Kelvin. Now on a sketch of this graph, this is going to be a little curve that goes to state 2. This is the state 2 here. Now the pressure obviously increased. It increased 3 times, but the volume decreased. Why? Because the gas was compressed. And this was for the part A of the problem, and the part A of the problem is solved by completing the sketch and explaining that this is happening at a constant temperature, so T equals constant. Now for the part B of this problem, this is going to be a little bit more difficult. We need to find the work done for this kind of compression. So we need to start from some general law. In this case, the work is being expressed as an integration over volume, pressure as a function of volume times differential of volume. So here we need to find a function that relates pressure and volume, and this function can be derived from the ideal gas law. So P times V equals nRT, and therefore P equals nRT over V. So we can substitute that back into the integral, where the work done is being equal to, these are constants, so number of moles, constant R, and temperature T, these are constants. They're going to be outside of the integral, and the integral itself will only integrate 1 over V dV. This is a table integral, so the result of this kind of integral is going to be always, so the integral of 1 over x dx is going to be ln of x plus c. This is for an unbounded integration, but for a bounded integral we'll have a difference. So the result of this integral is going to be nRT, and here we will have a natural logarithm as a solution for the integral of V2 minus natural logarithm of V1. From the rules of natural logarithm, we can transform this into a different form, where we will have a natural logarithm of V2 over V1. And we now need to relate this ratio here to pressure ratio. So this can be also done since the gas is ideal. For ideal gases at isothermic compression, like here, we know that V2 over V1 will be equal to P1 over P2. This means that pressure and volume are inversely correlated, inversely proportional. So we can further say that the work done is equal to n times r times t natural logarithm of P1 over 3 times P1, because P2 is equal to 3 times P1. This is given in the problem, so this will cancel out, and we can simply substitute that 2 times 8.314, then multiply with the temperature, which is 338 kelvins, multiply with the natural logarithm of 1/3, is going to be a negative number, since logarithm is below 1 gives negative number as a function, and the dimensions are going to be in joules, since we're only dealing with elementary SI units. Finally, the answer is the work done. When we put this into a calculator, we obtain that the number is minus 6,180 joules. This is the work done. And of course, the work is negative because we are compressing the gas. We're putting work inside the gas, and the gas is going to rise in pressure and decrease in volume. Of course, this is also all happening at the constant temperature. I hope this helps. The problem is now complete, and I hope to see you in another lesson. Bye.